Module 6 homework is fairly quick, but it should give you an idea of the types of problems that will be on the quiz. So we'll start with number 1. How much heat in joules is required to raise the temperature of 11.7 grams of liquid water? So we're looking at H2O with a little L. And we are going to raise that temperature by 20.7 degrees Celsius. So that is our delta T. And we're looking for a heat. Just enter the number. The expected unit is joules. We're going to be using the equation Q equals M capital C, which is the specific heat times the delta T. Now, if you can't remember this equation, that's okay. Specific heat of liquid water is 4.184, and then look at those units. The units for specific heat are found right here, and they are joules per gram degrees Celsius. So if we use our dimensional analysis and we want to end up with joules, we need to cancel out grams and degrees Celsius. So multiplying by the mass, 11.7 grams, we'll cancel out grams, and then multiplying by that change in temperature in degrees Celsius, 20.7, we'll cancel out that degrees Celsius, and we will be left with joules. So all we have to do is multiply this all together. So 11.7 times 4.184 times 20.7 will give the heat. Now this is for my problem. Your problem is highly likely to have different numbers. So the Q is 1013 joules. Now this system is a little bit strange with significant digits. Because our measured quantities both have 3 significant digits, we should only be reporting 3 significant digits. So 1010 joules would be 3 significant digits. However, because our system is really weird, I would just put in the 1013 and call it a day. Remember, I do grade all assignments manually, so if there's a little bit of adjustment there, I can make that adjustment. Number 2, the delta H of formation of rust, which is Fe2O3, has a heat, or the enthalpy is negative 826 kilojoules per mole. Now, to be abundantly clear, the standard enthalpy of formation is the change when exactly 1 mole of a pure substance is formed. So we do not need stoichiometry for this one because this is the delta H of formation. So we're going to start with 13.69 grams of rust, Fe2O3. Now, 99% of the time you see grams, you convert it into moles. So we're going to need that molar mass. 1 mole of Fe2O3 has a mass of 159.69 grams of Fe2O3. Now, if your molar mass deviates slightly because your periodic table is a little bit different than mine, that's okay. Again, I do grade these manually. It shouldn't be deviating much. These are the only digits that should ever be changing based on different periodic tables. So now that we have moles of Fe2O3, how do we get the energy? Well, we need to use this heat of formation, 826 kilojoules, because kilojoules is what I'm expecting. It says the expected unit is in grams, and that is incorrect. I'll have to get that changed. But that is per 1 mole of Fe2O3. So then to complete this calculation, it's 13.69 times 826 divided by 159.69. So we get 70.81. Our measured quantity has 4 significant digits, therefore we would report 4 significant digits. So 70.81, and I will get that expected unit tag corrected. So 70.81. Then using the standard H from the tables. So what is the heat of the reaction? So the heat of the reaction, you need to have a balanced equation. We have Cr2O3, and that is a solid. This is where having these phase tags is very important because we do have different heats associated with different phases. And I'm going to just write down this equation as quickly as I can and still keep it legible. Now we need to balance it. So looking at chromium, because chromium is over here and alone, I'm going to do chromium last. I'm going to start with carbon. The carbon is balanced, so that's an easy place to start. I have a total of 4 oxygen atoms on the reactant side, so I need to put a 2 here, but putting a 2 here puts a 2 here because I have those carbon atoms. So that changes my oxygen, and that changes the oxygen into, so I'm looking at oxygen here, and I'm going to be balancing the carbons and the oxygens. So the oxygen on the reactant side, now I have 5, and I have 4 over here. So what that tells me is I really need an odd number here. So if I put a 3 here, then I have 6. So in order to get 6 here, I need a 3 here. Now that does balance my carbon atoms. I have 3 carbon atoms on my reactant side and my product side. And for the oxygen atoms, I have a total of 6 carbon atoms on the reactant side and the product side. I have 3 oxygen atoms here, and now I have 3 oxygen atoms here. So the carbon and the oxygen are both balanced. Chromium's easy because he's alone. So put a 2 here. So for the delta H of the reaction, what I'm going to do is use the equation that the sum of the H of the products minus the sum of the H of the reactants. This is where we're going to be using our stoichiometric coefficients. Now, because I have this open in a small window, I'm not sure I can change the size of that window. I cannot. This is going to be a little bit tricky. But I'm going to just scroll down, and I'm looking for chromium. There's chromium. So chromium solid, and it's conveniently, it's the first column that I'm looking at for the delta H. And I'm just going to write my H values under here just to keep them safe or keep them in one place. So for chromium as a solid, it's a 0. For Cr2O3 solid, it's negative 1139.7. And all of these units are going to be kilojoules per mole. And then I need carbon. Scroll up a little bit. I need carbon monoxide, CO. There we go. And I need CO2, carbon dioxide, both in gaseous form. So CO is negative 110.52. CO2 is negative 393.51. Now I can use the stoichiometry. So the sum of the products as they have been multiplied by their stoichiometric coefficients. What does that mean? That means I'm going to take this 2 and multiply it by 0, and then I'm going to add to that 3 times this. So 2 times 0 is 0, that makes it easy, plus 3 times, don't drop the negative, 393.51. So that is the sum of the H of the products. And from that sum, I will subtract the sum of the H of the reactants. What does that mean? That means I'm going to take 3 times negative 110.52, and let's use purple. Then I'm going to multiply that by, and then remember the absence of a number in a balanced chemical equation is a 1 and not a 0. So 1 times, don't drop the negative, 1139.7, and add to that 3 times negative 110.52. When performing this calculation in your calculator, I strongly recommend that you use parentheses. Now 2 times 0 is 0, so let's just forget that part. And then with this particular calculator that's came with my computer, you have to enter the number and then add the negative sign. But work your calculator your way as long as you get the correct answer. So we're going to subtract from that the sum of the reactants. So I'm going to go 1139.7, change the sign, plus 3 times 110.52, change the sign, close the parenthesis, and I get a total of a positive 290.73. Now the units for this are kilojoules because these numbers represent moles. So this is the delta H of the reaction is in kilojoules. So I would write 290.73. Now specifically, because we're looking at these values here and we are doing some subtracting, I would have to go to the tenths place only. So if you only represent it like that, that's okay with me. Then we have the building questions. So what I'm doing is I'm trying to prepare you for the final exam as we move forward. So we start with the problem that we had in Module 5, and what we're adding is the standard enthalpy of formation of the reaction and the heat generated from the reaction conditions as identified above. Okay, so I have my balanced chemical equation here, and these are all gases. How do you know that? Well, C2H4 is a very light molecule. It is covalently bonded. It has, we haven't done intermolecular forces, but that's something, we'll do intermolecular forces in the next module. However, it has the weakest of the intermolecular forces, and therefore it doesn't hold together as a liquid. It's a gas. Because we start here as gases, we can assume that we end with gases as well. So they are all going to be gases. And then we're going to need to find the H, the delta H, or the H of formation for each of these compounds. So here I'm going to go CO2, which I just used, is negative 393.51. Then I have oxygen, I have water. Oxygen is going to be 0 because that's its elemental form. But what about that C2H4? Let's see, what do we have here? C2, there we go, there's C2H4 is 52.4. And again, the units for this are kilojoules per mole. And now I'm looking for water. So it was faster to just search. Now I'm looking for gaseous water, so I need to make sure that I am using the correct phase, negative 241.82. Now the H of the reaction is going to be the sum of the H of the products minus the sum of the H of the reactants. And this is where we use our stoichiometry. So I'm going to be multiplying 2 times this value, and I'm going to be multiplying 2 times this value, and then they get added together. And let's see, 3 times 0, that's probably my favorite one. And let's use this color, why not? And then remember, the absence of a number is a 1 and not a 0. So 2 times negative 241.82 plus 2 times negative 393.51. And then I subtract from that, because these are my products and these are my reactants. I'm going to leave the 0 out just for brevity. So 1 times 52.4, and I perform that calculation, and I get a value of negative 1323. Looking at sig figs here, I would go to the tenths place because of him. So 1323.1 kilojoules should be the heat, the standard enthalpy of formation. So what is the heat generated from this reaction conditions as identified above? Well, this is the kilojoules per this reaction. So how many moles? Let's start with our limiting reagent. The limiting reagent was the 200 grams of oxygen. So that is what's going to prevent any more energy from being produced, because once the oxygen is used up, we can't produce any more energy. So again, 99% of the time we see grams, we need to convert that into moles. 1 mole of oxygen, diatomic oxygen, has a mass of about 32.0 grams. And then we're going to use this. Now, how do we use this? Well, we have this negative 1,323.1 kilojoules. But what is that per? Well, that is per the balanced equation. So 1,323.1 kilojoules can be produced when we have 3 moles of our oxygen. So now we are using our balanced chemical equation. Let's just double check our dimensional analysis. Grams of oxygen cancel with grams of oxygen. Moles of oxygen cancel with moles of oxygen. And we are left with kilojoules, not kilograms, I need to eat. So when we perform this calculation, we have our 1323.1 across the top, and we're going to multiply that by 200. We then divide that by 32 and 3 and get that we will produce negative 2,756.4 kilojoules of energy with these conditions.